Okay, so let's start with the first session of contributed papers to the STARK conference. My name is Kamal Lodaya, and let me welcome you all to this session. So there are going to be 3 talks in the session. The first one is on RE axiomatization of conditional independence. It's by Pavel Naumov and Brittany Nicholls. They're from McDaniel College in Westminster, but not in London, right?
No. I wish. So this is talk on conditional independence, but let me first explain what independence is, what I mean by independence. If we have 2 variables, in such way that any value of the first variable can be matched with any value of the second variable, then I say that those 2 variables are independent. For example, the height of a rectangle is independent from the width of a rectangle. Whatever height you pick, whatever width you pick, they can happen together. This is not true for, say, area and perimeter of triangle or rectangle. If you have triangle with perimeter 3, it cannot have area 100. The triangle can have area 100, it can have perimeter 3, but not simultaneously. So we'll say that height and width are independent, but area and perimeter are not independent, and this is my notation for not independent. Parallel bar is for independent. Another example of independence is when you have a text and encrypted ciphertext using one-time encryption pad. Then there is absolutely no connection between the original text and encrypted text, and therefore any 2 pairs of them, or any pair of them can happen. There's a clear epistemic meaning of independence. If you know value of height, there's absolutely nothing new what you learn about value of width of rectangle. So if things are independent, then by knowing one, you learn absolutely nothing about the other. If they are not independent, then by learning one of those values, you learn something about the other. Independence could be defined, independence was first introduced by Sutherland in 1986, and it's sometimes referred to as non-disability. You can also generalize independence to a relation between 2 sets of variables. And here's an example. If we have 3 variables A, B, and C, and we know that A, B, C are any 3 numbers such that sum of them is even, then, of course, A and B are independent because, A is whatever, 5, B could be anything. By adjusting C, we can guarantee that sum of them is even. At the same time, A is not independent from BC. It's not true that you can pick any legitimate value of B and C and combine with any value of A. Right? If A is 1 and B and C both 0, then sum will not be even. So the 2 sets are independent if any legitimate combination of values on the left is compatible with any legitimate combination of values on the right. More formal definitions, we have set of variables, like sometimes in secrets. A protocol is just specification. What kind of values those variables can have, and what are the legitimate combinations. Those legitimate combinations of different values of variables will be called runs of a protocol. 2 sets are independent if, well, you pick certain run from one set, another run for another set, those values can happen together on a third type of run. So you pick a width from one rectangle, height from another rectangle, they can happen together on a third rectangle. Well, naturally the question will be what are the properties of independence? And turns out that there are 4 basic properties. First 3 of them are trivial. Nothing is independent from something, and with monotonicity, if something big is independent from you and small is independent. And so symmetry, the only interesting property here is exchange. Axiomat allows us to move variables from left to right side of independence. Common here and everywhere below stands for union of sets of variables. So A, B, and C are sets of variables, and comma is just the union of those variables. It turns out that this system of axioms is sound and complete with respect to the semantics I just described. But what is maybe even more interesting, that the same axioms actually describe other relations. And originally, those axioms appeared in the work by Geiger, Parson, and Pearl in 1991, when they looked for axioms for independence in probability theory, the statistical, stochastical independence. It has exactly the same properties, and the system of axioms is complete for this probabilistic semantics. It also turns out that the same axioms are complete for non-interference relation between concurrent processes, and it's also complete for interchangeability of Nash equilibrium relation, which is a very old relation from game theory that goes back to one of the original Nash's papers on Nash equilibrium. What I will talk about today is a generalization of this notion of independence to conditional independence. Let's suppose again we have some secrets. This time maybe 4 secrets, A, B, C, and D, and we know that some of them is even. Then again, A is independent from B because you can fine-tune C and D to make this happen. I also will say that A and B are independent conditionally upon C. Conditionally means somebody announces what value of C is. Now everyone knows what it is, and we only consider combinations of tuples for which C has a specific value. This way, the set of all possible runs of a protocol is reduced to all runs with this fixed value of C. If after you fix C, A and B are still independent, then I will say that A and B are independent conditionally upon fixed value of C. We know that A is independent from BC in this case because there is a D, and so you can adjust D to match any value of A with any pair of values of B and C. This is no longer true if you look at conditional independence with condition D. So if somebody tells you that D is 25, and you now look only at tuples where D is 25, then A is no longer independent from D and C. Right? A is 0, then B and C cannot both be equal to 0. So that's the relation which I want to take a look at. Conditional independence, when you fix one or maybe several variables, assign them specific values, and see if there is a dependence between the rest of values. What are the properties of this conditional independence relation? Well, you can take the properties of unconditional independence that we discussed earlier, those 4 properties, and kind of relativize them with subscript. The trivial way to do it is just putting subscript empty set. Right? So this is the most interesting axiom that I discussed before, exchange axiom. If I add empty set everywhere, and it means, well, I don't fix anything here and don't fix anything there, and so on. That's still true. That's a property of conditional independence. Not a very interesting one because it really focuses on what we discussed before. You can make it slightly more interesting by noticing that this is actually true for every fixed subscript. If you fix D all the time, that's still true. Still nothing really exciting. What will be interesting is to see if there are properties that would allow you to move variables from subscript up or down. And it turns out, yes, there are such properties. One of them says that you always can shift a variable from up down into subscript. So if you have independence, A and B together is dependent from D conditional upon C, you can condition B, fix B, and A and D are still independent. This is a relatively easy to see property if you think what semantics of this is. Now, can you move it back from subscript up? Well, not always. You need to have extra condition. So in this case, what I'm trying to go from here to here, like I'm trying to move B up. And I can do it if B is C independent from the other side. So if my subscript is independent from the other side, then I can move my way. At some point I thought this is probably all there is to it. And there's a nice two properties. It would be nice to prove completeness. Then it was like 6 years ago. And things didn't really work out because it turns out that there are many more properties, and this is one of them. Really scary. No, I did not intentionally try to make something complicated. This is certain property written in as short form as possible. This is true. You can, yes?
Excuse me, I might have missed that. When you write conditional independence, can the sets A and C intersect? And if so, what is your...
You can assume, no, they do not intersect. So if they intersect, you need to if A and C intersect, then nothing really interesting happens because you already set C fixed. What becomes interesting if A and B intersect, and this is outside of my consideration. If A and B intersect, actually this is a functional dependency hidden there, and things get more complicated. So back here, we have this very scary property. And what else is interesting is that this relation, conditional dependence, it turns out have been studied a lot in the database theory, where it's known under not at least very intuitive to me name embedded multivariate dependency. And in 1980, Park and Parsik proved that there is no finite system of inference rule for this relation. So we no longer look at propositional formulas, just at the inference rules, how one independent statement could be inferred from another or from a couple of others and so on. And we proved that this relation has no finite system of inference rules. In 1995, Herman proved that implicational fragment or propositional theory of this relation is undecidable. He later found mistaking his proof incorrectly 10 years later. Well, the result that I want to show today kind of complements what you have here. They have shown that if there is a way to axiomatize conditional independence, then it should be a hard way, right? There's no finite axiomatization, really there's no decidable axiomatization. Well, what we proudly announce today is that there still is an axiomatization. It's not decidable axiomatization, it's recursively enumerable axiomatization. So we can structure an algorithm that will generate infinite sequence of axioms, and together this set of axioms is a complete set of axioms for this relation. There is no way for me to show you proof of completeness today, but I at least will try to describe how this procedure works, procedure to generate those axioms. At the core of this procedure is the notion of diagram. Diagram actually appeared in those early works in the database theory, where people used them to explain why some formulas are true. What we did, we took this notion of diagram, formalized it, and showed that if you cannot show a formula is true using diagrams, then formula is never true. And that's the core idea behind proof of completeness and behind this work. Now, there is another more internal to me origin for notion of diagram. It's diamond principle. Some of you might still remember it. And if you don't, let me remind you. This is a slide from my talk a year and a half ago at TARC in Groningen, where we axiomatized a different relation using very unusual looking logical principle we call the diamond principle. Well, the notion of diagram actually generalizes diamond principle. If diamond is in some sense two-dimensional object, diagram is infinite dimensional version of diagram. Or at least that's how we look at it. So let me explain to you what is diagram on an example. I will show how we construct a diagram, and I will always construct diagram by starting with two vertices, V plus and V minus, connected by an H, in this case undirected H, labeled by some set of variables. Remember we have those A, B's, and C's, sets of variables, sets of secret variables. Well, those are labels now in the diagram. Any diagram is constructed using some active basic formulas of conditional independence. We will act to construct this diagram. So the first formula that comes into play is, let's suppose B is conditional independent from C upon condition A. Well, I have two vertices here on this diagram which are A connected. And each time when I have this acting formula, I create another vertex, a child vertex of those two, and I label those two connections with BA and CA. So I take kind of this side and this side, and that's how I label it. Let's suppose now we introduce another acting formula. Well, subscript here is B, so I can find any two vertices here which are B connected. For example, V plus and V1, and pull down another child and label this edges leading to this child in the same way. Let's suppose we introduce another acting formula, and again, subscript here is C, so I find something which is C connected and pull down the child. Another acting formula, subscript is D. I can pull a child from V1 and V2, but I will do something more interesting. When I say connected, it doesn't have to be directly connected, just enough to have a path from one to another. So I will pull down a child from V2 and V3. Those two vertices are deconnected, and that's my diagram. So this is diagram, and this is acting set of formulas. For every diagram, there is a unique acting set of formulas that created this diagram, but not vice versa. If you have a given acting set of formulas, you can create multiple diagrams from it. Now, the next is the most confusing slide of the talk. So if I lose you, let's expect. So we'll say that there is a diagram, and a tuple of length 10, then we say the diagram renders this tuple if, well, this is the original vertex, V plus and V minus, from which we start to construct the diagram. The diagram is assumed to be larger, but somewhere inside this diagram is W1 and W2 such that, well, those two are connected by this type of path. Those two are connected by this type of path. When I draw a double line over here, what I really mean, I don't have to have a single path for all of those guys. For each variable in this huge set, we have a separate path. So it's a big break connected to two vertices. So if I can find in my huge diagram W1 and W2 such that this is true, then we'll say that this diagram renders this huge tuple. Okay, well that's all what you need to know in order to see our infinite list of axioms. First axiom is symmetry. So if you are independent from me, but I'm independent from you, that trivially follows from definition of our semantics. Maintainability is also very simple. And finally, the monster. Here's how we read it. If we have a diagram, delta, and there is a tuple rendered by this diagram, then conjunction of all acting formulas that we use to construct the diagram implies this very, very tricky permutation property. You see, what it does over here, it switches chunks of sets from left to right, from right to left, from subscript up, and so on. I'm not trying to make it more complicated than it is. I try to write this principle where you can just make one single move. It doesn't work. In order to have a complete system, you need to be able to make all moves in all possible directions simultaneously, and that's why it's so hard and complicated. So this is the axiomatization. Why it's recursively enumerable axiomatization? Because anyone can just enumerate all possible diagrams. And for each diagram, you can see, just one second, you can see if a given tuple is rendered by this diagram. It's a decidable property. And afterwards, if yes, then you write the next one. Yes?
D can be arbitrary.
Yeah, D is the thing which disappears, but it doesn't mean that you can just arbitrarily drop D in subscript. You see, D is a part of this rendering property. So, yes, you can remove D, but under certain circumstances, if it happens in the right place in the diagram. It's like altogether, and there is no way to, at least known to me, way to pull it aside. Let me show you some examples of properties that we can prove from this, these axioms. This is actually one of the properties I mentioned in the beginning, how you can move something to B from subscript up into the right-hand side. It turns out this is a special case of this diagram axiom. Namely, let's look at this very basic diagram, right? We have two vertices and we just create one child. If you look very carefully, then there is actually a tuple rendered here. Remember, I was supposed to give you W1 and W2. Well, in this case, W1 is V1, but W2 is actually V minus. So V minus serves as two different corners of a rectangle with a this rectangle. It's V minus here and V minus over here. If you go look at the definition of what renders means, then it turns out that this tuple actually is rendered by this diagram due to this observation. And then by diagram axiom, we have something like this. With only one acting formula, which was used here. We have only one child. This acting formula is A and B are independent, conditional on C. And that's it. What I promised is what I got. Another example. This is where you can shift B down in the subscript. If you remember, it was a free property. With no extra assumption here, you can always do it. We can prove it using our diagram principle. And it turns out here, the diagram is trivial. It has no children at all. You just start with two vertices, that's it. This thing renders something like this. So this is V plus, and this is V plus again, V minus again. And because it renders, well, it renders this tuple, we can write diagram axiom. This conjunction is true because it has no conjuncts. This is a trivial diagram, has no children, so there are no acting formulas. And so set of acting formulas is empty, conjunction of empty set is true. Therefore, this could be written as just this, and we're done. Now, at this point, you can, well, okay, one more example. This is this monster that I have shown in the beginning. There should be a reason why I did it. Indeed. This diagram which we discussed earlier is exactly the diagram that proves this monster. If you have enough time, you can notice that this diagram renders this tuple due to this picture. We pick, so this is our, over here, V plus serves as here and here, and this is V4, it's this guy. So 1, 1, 1, 2, and 1, 2, 3, and 4. Those are 4 vertices. We render this tuple, and then by this diagram axiom, we have this application. There are 4 different formulas which we used to construct this diagram. We went over construction 20 minutes ago. If we put all of them out, we get exactly the theorem that I promised in the beginning. Now, at this point, you might think that to prove anything in my theory, I just need to use the right diagram. No. In reality, to prove some propositions, you actually need to use logic, you need to combine some of those axioms. So as a simple example of such proof, let me prove you this exchange property for independence without condition, but without condition means condition is kind of set. This is something that we did. This is our first example where we have shown we can move things down into subscript, and I have shown you how to do it with the diagram. In our second example, what was to move it up, or actually maybe the other way around, but okay. I think this was the second example, this is the first. But anyway, if you now look at this formula and this formula, when you realize that this is just a logical combination of those two below. So this proof now is using 2 different diagrams, one for example 1 and another for example 2, combine them together and gets what we want. Okay, so this is a summary of what we had. Before, people showed that essentially our task is hard, right? There's no easy optimization, and we found one we found, and recursive enumerable, which probably is the best that could be found here, because we know a set of statements is undecidable. So it cannot have this, well, wait. If you remember the beginning of my talk, you can ask, what about the other independence relations, like in probability theory, in game theory, or in concurrency? Well, for probability theory, once you don't go to conditional independence, this my type of independence and probabilistic independence become different. So there are examples of formulas which are true in one case and false in another, and in particular, our diagram principle is not, as I understand, is not true for conditional probabilistic independence. There are some partial results for conditional probability independence, again, negative results on how hard potential axiomatization could be, but there is no known axiomatization as we speak. And for other semantics, concurrency, and game theory semantics, I just find this question not interesting, because if you start thinking about conditional independence, say for game semantics, it doesn't really mean anything natural. You can introduce this relation and you probably can study it, but it's not clear why you want to waste your time doing it. My bet would be that for game theory, you probably will get the same axioms as in my today's talk with this diagram axiom. And for concurrency, I just even don't know how to define it nicely. But yeah. My conditional independence has no probability in it, right? 2 facts are independent. This thing could be matched potentially with this one. In probability theory, we say that 2 facts are independent. If product of probabilities is equal to probability of intersection, it means that if those 2 things happen often together, but they are not independent. They still could be independent in my sense, but they will not be independent in their sense. So it's a different notion, and the properties that this notion has on unconditional level are the same. On conditional, they're different. They're examples of formulas which are not my examples from literature, which are true for one reverse relations and not true for one. I don't know if I answered the question.
Your logic, was that known to be recursively enumerable before you proved it? The result you just gave, was that known before you gave the axiomatization?
Was known?
Yeah, was it known?
No, I'm not aware.
Ah, no, okay. So,
Was it known that it's recursively enumerable, but maybe not with...
Oh, no, I'm not aware of any result.
Okay. You might imagine a translation argument would be possible instead of giving the actual axiomatization.
Translation into something else.
Yeah, exactly, yeah.
Yeah, but I don't know the right...
No, I had
Well, this was actually very much the same question or follow-up to it. I mean, the natural translation is into first-order logic, and it seems to me that you can actually define in first-order logic this notion of independence. And so then one would expect recursive axiomatization. Yeah.
Natural translation into first-order logic?
Yes.
In which sense?
Well, independence means that basically the set of pairs, let's say, talk about two variables. So the set of values would be union of rectangles, so to speak, right?
Yeah, but
So you can express this in first-order logic. That's how it seems to me. I might be wrong, of course, but
it's not quite clear because we talk about sets, right? We A, B, and C as sets. First-order logic normally doesn't deal with sets.
yeah, I don't mean to embed a whole set theory there, but just as much as you need. I mean, you have your domains as part of your first-order structure, and then you have a relation of independence. And, well, again, I'm not claiming anything, just asking or suggesting, and it's essentially it's follow-up to Torben's question.
I think it's close. I need to carefully. I didn't really. I mean, I was more looking for specific axiom. That's why. I need to think about this more for.
Okay. Yeah.
Okay.
No, I had a different question, which is it possible to reason about a larger diagram from smaller diagrams? I mean, from some property of the smaller diagrams, you get something with the larger diagram.
Probably yes, because the key relation is rendering, right? If you can render something in a bigger diagram using only subset of this diagram.
Yeah. So then you might get recursive axioms and a finite inference rule. That's possible.